All right. Thanks everyone for joining today. Excited to share with you all something that I've been has been sort of a pet project for me over the past several years that I've come back to, and it's setting thresholds for the RMS-Energy oscillation detector. The reason I've been looking at this for a while is that this detector, this particular oscillation detector, is one that's used in commercial tools. So it's pretty widely used by industry, both in electric power groups, real-time dynamics monitoring system, RTDMS, as well as the Schweitzer Engineering Labs' synchro-wave operations. So it's used in those commercial tools, and so quite a few utilities use the RMS-Energy oscillation detector within that software. And so what I've wanted, my goal has been to be able to kind of come alongside those platforms and provide people with a tool that would set thresholds that are very meaningful. And what I mean there is that they're thresholds that avoid nuisance alarms, so your operator's not getting alarms that are for really small oscillations that you don't want to know about, but also provide you with predictable performance so that you know ahead of time what type of oscillations you will be able to detect, and to do this in a way that is a little bit more convenient than what we have available today. And so those have been my goals, and so that's what I'll focus on today. This presentation, I'll kind of take you with me on the journey. So I'll start with some of the things that motivated me initially, and some of the earlier approaches that I had to this. And then I'll spend kind of the second half of the presentation focused on this newest approach I have that I think kind of checks all these boxes that I just mentioned for the things that I was trying to make it do. Throughout the presentation, I'll to demonstrate some things, to highlight some concepts. I'll show some results that are from field measured PMU data that are in a tool that we have here at P&L called Archive Walker. That tool is really, it's a research tool. It helps us to develop things. So it has an RMS-Energy detector in it, so you'll see that. I just wanted to make it clear from the beginning that my focus isn't on that tool and trying to talk about that tool and its capabilities. I'm just using it to demonstrate things. The real focus is on the methods, and hopefully making those available to utilities eventually. So with that, I'll dive in here and start with a little bit more on the background and motivation. The project that I've been working under is one that also led to the development of the Eastern Interconnection Situational Awareness and Monitoring System, or ESAMS. And that tool was developed to monitor an interconnection. So here we're looking at like the entire Eastern Interconnection, and detecting, when we detect an oscillation, what we want to do is determine which reliability coordinator that oscillation is coming from. That's the goal of ESAMS. And so it's meant to coordinate with the internal tools that a reliability coordinator has. We say which region it's coming from, and then everybody would use their internal tools to identify the particular source. This tool was co-developed with the electric power group, and with that background, it contains two complementary oscillation detectors. One is a periodogram-based detector that we developed at P&L, and the other one is the RMS-Energy detector that is part of EPG's real-time dynamics monitoring system, or RTDMS. Currently, ESAMS is deployed at Southern Company, and one of the things that Southern Company was really interested in for the deployment was comparing ESAMS, particularly the periodogram-based detector, against their existing RTDMS deployment. So ESAMS has RTDMS kind of as a component, but then Southern Company also had a standalone RTDMS deployment. And so they wanted to look at what types of oscillations the two tools would detect, how they did the localization of oscillations, and that sort of thing. So that was the goal there. And so this gave me the opportunity when we came in and started this project to set up thresholds in RTDMS. And so I was able to revisit this work on how to set thresholds. And that's what has led to this most recent approach that I'll be sharing today. A little background on how the RMS-Energy detector works. In the diagram in the upper left, that signal Y is PMU data. So it could be voltage or frequency, but here I'll focus on megawatt signals. The other most common one is reactive power signals. So throughout here, this presentation, you'll be seeing megawatts. So you take in that PMU signal and then use some signal processing shown at the bottom in that band selection portion, where you do some anti-aliasing filtering, decimation, and a bandpass filter to take that signal and basically break it into four new signals, each one of which has frequency content, and the range is shown in the table. And then finally, you implement the RMS calculation using a moving average filter for the averaging. So what comes out of the detector then is you have these 4 RMS-Energy signals that are for each one of your megawatt signals, and you're comparing them against a threshold to determine when an oscillation is present. And that's what this is showing. In the top plot, we have the input data. So this is a megawatt signal where I've added on an oscillation here midway through. And you see there's the dramatic increase in RMS energy. It goes above that threshold that I've set at about 4 megawatts. And but then importantly, with these detectors, they don't issue an alarm as soon as that threshold is crossed. In the practical detectors, we always wait for it to stay above the threshold for a certain amount of time. In this case, for band 2, I think band 2 is the 0.15 to 1 hertz, so in the range of electromechanical modes of oscillations, that's an important band. For band 2, typically wait, I think the typical setting is 30 seconds. And so you wait 30 seconds, and that's what's shown at the bottom is that's a counter that it starts at 0 and it counts up to 30 seconds. And once it's stayed above the threshold for 30 seconds, that's when detection occurs. So this is the way that an RMS-Energy detector works. And so this presentation is really about how do you set that threshold in the middle plot, that 4 megawatt threshold. Again, we want to be able to detect oscillations that we're interested in while avoiding any false alarms or nuisance alarms. I'll make that distinction between false and nuisance alarms throughout the presentation. False alarms, it's a really clean definition of where there are no oscillations present, so it's just ambient conditions. But for nuisance alarms, what it counts as a nuisance alarm is really up to the user. But all I'm getting at there is that it's an oscillation that is too small to be of interest to that particular user. So you could imagine a control room where if you've got a 0.5 megawatt oscillation and someone is monitoring a big portion of an interconnection, that may not be of interest to them, a really small oscillation. So that could be but if they're being notified about that over and over and over again, that would become a nuisance. For a researcher, maybe that threshold is different or much lower. So it really depends on the user, but that's the distinction I'm making is a false alarm is where it's truly ambient conditions. A nuisance alarm is where it's just a small oscillation that you don't want to be alarming. Okay, so now this is where I'll jump to Archive Walker to, I need to hide some of this stuff so I can see. I'll show some results here. So these are all, everything I'll show on Archive Walker it's field measured PMU data under ambient conditions. And then in some of these later examples, I'll add oscillations so that we can talk about some different things. But for this first one, I just want to talk about the simplest case that you could do for how do we choose that threshold that I just showed, that 4 megawatt threshold. How do we choose that? The simplest thing you could do is just use a default for all your signals. So here I've got these 4 megawatt signals coming in, and I'm going to set this threshold at 2.12. Where does that come from? So I'm going to use, let's say 3 megawatts. We want to detect 3 megawatt oscillations. And so the RMS of that, square root of 2 over 2 times 3 is 2.12. And then I've got this duration threshold of, or duration requirement of 30 seconds. So now let's go and look at an hour of results here. I'll just zoom in on a portion of this so we can look a little closer. Okay, so now here, again, we've got our 4 signals. When I click on these tabs, I'm choosing between those 4 signals. And here, just like in the plot I showed earlier, we've got our threshold with the RMS energy in blue, and then down here is our counter. So when we get up to 30 seconds, that's when, this is 30 seconds. When we get up there, that's when we'll trigger an alarm. So for signal 1, this threshold is actually pretty good. We don't have any false alarms in this 15-minute ambient period. We are crossing the threshold sometimes, but not for long enough to have any false alarms. But if we look at signal 2, this one, the RMS energy, just based on the natural characteristics of this signal, where it's located in the network, has more noise in this frequency band. And so it stays above that threshold of 2.12 basically all the time. So constant false alarms. Signal 3 is the opposite of that, where it's very low ambient noise in that signal all the time. And so it never even approaches the threshold. And signal 4 is sort of in the middle, where we get these 4 false alarms over the course of 15 minutes. So my point here is really just that with default thresholds, you can run into this where there's maybe more diversity in these signals than you might expect. All 4 of these signals are coming from the same reliability coordinator, and but they're based on where they're at, they look quite a bit different. And so setting just a one default threshold for all your signals is would probably lead to quite a few false alarms. And that's something that is very well known by industry. And so for years, there have been approaches to set custom thresholds for each signal so that you don't end up with all those false alarms. And so the current industry practice, or at least one of the most common industry practices, is reflected in this NERC document put together by the Synchronized Measurement Working Group. And what it recommends is calculating the RMS energy for historical ambient conditions. And then based on that, you set a threshold as the mean plus 3 or 4 standard deviations. So it's a really intuitive approach. It's got some engineering judgment behind it, and this is what's used today. One of the challenges here is so it does need to be applied to ambient data, and it doesn't this NERC document doesn't go into a lot of detail about how much data used to establish that mean and standard deviations. But it does talk about how once you set that threshold, then you want to go back to at least 3 months of historical data and review it. And so it talks about kind of this iterative process of seeing, what types of oscillations are you detecting, what did you miss, and so it requires a lot of work to go. You can imagine if you're trying to do this for hundreds of signals, right? There's some significant effort here. So there's that aspect. The other thing about this, for me, I come from a background where I'm using statistics to do this, and so when you talk about the mean and standard deviations, if you have a Gaussian distribution, we know what that means for probabilities, but in this case, we don't have that at all. So it's a rule of thumb, but there's no real statistics that's statistical theory that's really driving this. And so the first thing I did was I wanted to take a really theoretical approach to setting thresholds to avoid false alarms. And so that resulted in the paper that's cited at the bottom of the page. And the way that we approached this is we looked at the RMS and the RMS of a signal, and its equivalent in the frequency domain using the periodogram. So a periodogram, it's where you take the discrete Fourier transform of a signal, and then you take the absolute value and square it and scale it. That's the periodogram. And so this equation that I'm showing there is showing the relationship between the energy in a signal in the time domain versus what it looks like in the frequency domain. So the reason that we do that is that we don't know much about the statistical properties of the RMS energy, but we do know a lot about the statistical properties of the periodogram. And we can use those then to set a threshold that will, where we can set a limit on the probability of false alarm. So the user gets to choose and say, I want a probability of false alarm of 0.00001. And here is the threat. And by analyzing the signal, in the frequency domain, you can choose a threshold that will achieve that. But there are some qualifications on that. This threshold, it's that probability of false alarm is not taking into account that 30-second duration requirement in practical detectors. It's just crossing the threshold at all is considered a false alarm. It's a theoretically rigorous approach. So there's some really nice theory in that paper, but it is challenging to implement. You run into numerical problems that you have to work around and be very careful about. It's also, there's many details that you have to get just right for this to work. So it's challenging to implement. And the biggest challenge with this one that I'll talk more about later is that you can set a limit on the probability of false alarm, but you can't we can't say anything about probabilities of detection. So that means we can't say what the probability is of detecting an oscillation that you are interested in. It also means that we can't set thresholds to avoid nuisance alarms. And so there's the drawback there. And again, I'll talk more about that later. But first, I'll go back to Archive Walker and let's just look at what it looks like to set some custom thresholds. And so this now, actually, let me go back to my settings here and I'll show. So now instead of one detector, I've got 4 of them, and each one is using a custom threshold here. And again, we'll look at that same. So this is the same data, same 15 minutes, but now with updated thresholds. And just really quickly, I'll show now for each one of these signals, again, they're low enough that that the threshold is being crossed some, but not for 30 seconds. So no false alarms here, no false alarms for signal 2, no false alarms for signal 3, and so on. So we can, using either of the approaches that I just described, you can pretty effectively avoid false alarms. But this is where now we need to start thinking about nuisance alarms, because practically for if you're operating a power system, again, you don't want to be notified about every little oscillation. And so so it's not enough to just think about from a statistics perspective where you can do the theory for false alarms. It's important to be practical and also think about nuisance alarms. So what I've done here, these plots at the top, I haven't introduced them yet, but this is showing just 1-minute summaries of the RMS-Energy. And so really quickly, I'll show here, you can see these big increases every 5 minutes. Here, I've started to add oscillations to the signal, on for 5 minutes, off for 5 minutes, on for 5 minutes, off for 5 minutes. And each one of those, I'm changing the frequency. So you'll see a little bit of different behavior across those 5 oscillations just based on the frequency. Okay, so now this is using the same thresholds that successfully avoided false alarms, but now these for signal 1, I'm starting to detect this 3 megawatt oscillation that and in this case, I'm calling a 3 megawatt oscillation too small. It's a nuisance. Again, nothing magical about that 3 megawatts. It's really up to the user. But here I'm saying it's a nuisance to be detecting a 3 megawatt oscillation. So signal 1 detects it 4 out of 5 times. Signal 2 doesn't detect that one. Signal 3 here, again, just these signals are different from each other. So now signal 3 is easily detecting that 3 megawatt oscillation. And you can imagine even like a half megawatt oscillation would be detected very regularly by signal 3. So there's great potential in signal 3 to have lots of false or nuisance alarms. And then for signal 4, just get a couple nuisance alarms there. So again, we want to, this really motivated me to keep working on the problem, because I knew I had, when I wrote that first paper, I thought the theory was really nice, but I knew it had that limitation for practical use, that it's not enough to just limit false alarms. We really need to, again, also be thinking about nuisance alarms. Okay, so that was the next thing I worked on was with how do we avoid nuisance alarms. So to do this, I went back to that relationship between the RMS and the periodogram. And again, the limitation of what I had done before is that it really comes down to this sum of periodograms. where when you add those together, in ambient conditions, we know that statistical distribution. So you might be familiar with Gaussian or chi-square. Those are the statistical distributions. The type of statistical distribution I'm talking about. In this case, it's a hypoexponential distribution, which is really uncommon, but that ends up being what it is. But we know its statistical properties. But when an oscillation is present, that all falls apart. We don't know what the distribution is, and so we can't do anything with probabilities of detection. But we can continue to look at if we look at this sum, we can talk about its mean and variance. We can obtain terms for those. And so that's useful in that we can then translate from the right side of that equation to the RMS, and we can set some typical ranges for the RMS energy. So here it's not as theoretically rigorous where there's no probabilities associated with that, but it's just a typical range that we would expect. And that's what's shown on the right side is these trials along the x-axis. This is where I've just run a simulation with 1,000 different simulations, calculated the RMS energy in ambient conditions, and we can see that the formulas that I have from this in this paper, you can capture the typical range. So it's okay that there are some of these trials outside the limits. It's not a theoretical limit on the possible values. It's just the typical range. And so we can do that in ambient conditions, which is basically what we've been doing before. But then what's new and useful here is that we can also do it when there's an oscillation present. So that's in the right plot where we've added a 10 megawatt oscillation. Now we can still have a typical lower and upper range for the RMS energy. And that's what is where this paper goes beyond anything before it is with an oscillation present, we can have a pretty good prediction of the typical range of the RMS energy. And then based on that, we can set thresholds. So we can choose our threshold so that we avoid nuisance alarms and we try to detect things that we're interested in. We can have some insight on where to set that threshold. So this approach made some progress on being able to avoid not just false alarms, but also nuisance alarms. So I'll jump back to Archive Walker to show that. And here, unlike the others, I'm going to look just at one signal. So this is signal 4, which we've been looking at before, but I'm not going to look at the others, so we can focus in here on signal 4. And what I've done is I've added, in this case, I've added a 3 megawatt oscillation. Same thing, 5 minutes on, 5 minutes off. And what we see is from this result, this threshold is set nice and high, well above the range that this RMS energy reaches when there's a 3 megawatt oscillation. So we're successfully avoiding that nuisance alarm. And we actually used this method to set up thresholds at Southern Company for the evaluation that we were doing. But what we started to notice is that we were being very conservative with these thresholds. And so we would see larger oscillations. In this case, I've added a 6 megawatt oscillation, so twice as large. Maybe we want to know about 6 megawatt oscillations. But it's so conservative that even the RMS energy here is only crossing that threshold some of the time. And we were seeing that really the reason we were being so conservative is we were trying to keep this threshold above the RMS energy basically all the time, based on that approach that I had just shared, when really we need to take into account this duration requirement down here. And just to show that that's possible, here we've got, again, the 3 megawatt oscillation where I've lowered this threshold down, and now it's being crossed a lot more, but it's still not creating any nuisance alarms because of this duration requirement. So there's enough variation in that signal that we're not creating nuisance alarms. And now we can detect this 6 megawatt oscillation. So again, this is what we were seeing in the ESAMS results. We were seeing thresholds. We're like, well, we're being pretty conservative here because we're setting these thresholds so high, and we're missing some things that we'd like to be able to detect. And so we need to take into account this duration requirement to be able to set these thresholds really the way that we want. And so that that brings me to this this newest approach that I have, and how we approached it to be able to take into account the duration requirement that's in there for practical detectors. So again, the limitation of everything I've shared so far is that I was relying on the frequency domain analysis to characterize the input signals, and that means I couldn't take into account that time domain requirement on the RMS-Energy remaining above the threshold for a certain amount of time. So what we'd like to be able to do is really start with ambient data, and but then not if we only did ambient data, then you can only talk about false alarms. But we want to talk about nuisance alarms and predictable performance. So we want to add oscillations of various sizes to that ambient data, and then run the RMS-Energy with the duration requirement included, and then use that information to determine a threshold that gets us the desired performance in terms of nuisance alarms and detecting oscillations that we're interested in. But of course, the challenge here is obtaining that much ambient data. And so one of the kind of tricky concepts here is that even for a given power system operating condition, you can have different random outcomes, right? And so of course, if we're using field measured PMU data, we only ever see one realization. And so we end up having to look at a lot of data to see all the different operating conditions. And then on top of that, all the different random things that can happen for a given operating condition. So you want to hope, I mean, you never see the exact same operating condition twice, but let's say just 5 o'clock every day, even if you did have the exact same operating condition, there's enough randomness in the power system that you would see slightly different behavior. And so we end up having to look at a lot of data, and then you never really know if the measurements that you're collecting from the power system, whether there's an oscillation in there or not, because you're trying to detect oscillations. So if you have the wrong threshold, you may not see it. So it's challenging to use exclusively field measured data for this. And so here's the approach that I've taken for this. It's a bootstrap-based RMS-Energy thresholding method. So the idea here is we start with PMU data, so field measured PMU data, and we do the band selection. We get a signal that's band limited, band 1, 2, 3, or 4. And that's really where the process starts with that signal X. And what we do is we build a model for that signal. And this model is an autoregressive model. If you're not familiar with that, it's okay. It's just basically coefficients in a polynomial that describe how you can go from white noise to this band limited signal X. And so this is a well-studied problem. You can what I've used in this case is a least squares curve fitting approach to be able to find the coefficients for this autoregressive model. But the important thing is that once you have that model, that's when the bootstrapping comes in. And bootstrapping is an approach from the statistics literature where you take a sample, a random sample of something that you're interested in, and then you analyze that, and by understanding the statistics of that sample, then you can generate new realizations. And that's what we're doing. So again, in the model that we're building, it's white noise in, and our signal, this signal that we have out. So what we can do is now we can replace that one white noise realization with 100 of them, as many as we want, right? It's not actually limited to 100, and that's just what I'm using here. But we can generate white noise, pass it into that autoregressive model, and now we get 100 new realizations of that band limited signal X. So now we're increasing our view of what could happen. After that, that's where we add the oscillations and calculate the RMS-Energy, and that's what's plotted on in this plot. It's 100 of these realizations of the RMS-Energy where we're adding a 3 megawatt oscillation. And what's really valuable here is that because we've analyzed the signal and built a statistical model of it, we can actually get a better picture of everything that could happen. So it's not just what did happen, but what could happen. And so the red line there is where I've taken the actual RMS-Energy, actual band limited signal X from PMU data that we used to build all this, added a 3 megawatt oscillation, calculated the RMS-Energy. And you can see in our 100 realizations they become more extreme than that one that we observe. So this is the real power of bootstrapping, is that we get a bigger, more complete picture by doing the statistical analysis of the signal than the one time domain that we actually observe. So it's really powerful. That might sound like magic, but it's well grounded in statistics. So the next thing to do is, how do we use these realizations to actually set a threshold? And so what we do is we look at, this is again 30 seconds, so it's that full amount of time that would need to stay above the threshold to achieve detection. So if we set the threshold below the lowest point for all 100, then we'll have 100% detection. If 10% of those realizations drop below the threshold at some point, then they won't trigger an alarm. So we end up with 90% detection. And eventually we go high enough that all 100 realizations at some point drop below the threshold. And so we get 0% detection. So this is how we can choose a threshold and then evaluate what the detection probability will be. So in practice, I'm not doing this just for 100 realizations. I'm using, what I've done so far is I've used a 2 days, a 2-day period of data where I split it up into adjacent 20-minute windows. And this gives us a picture of different operating conditions throughout the day. And then 100 realizations for each one of those. So we build a new autoregressive model for each one of those 20-minute windows, and then 100 realizations. So in the end, I'm using 14,400 realizations to set these probabilities. And then I'm choosing a threshold to avoid nuisance alarms based on the user input on what would be a nuisance, what size oscillation would be a nuisance. So in this case, 3 megawatts, I'm saying, would be a nuisance. So I can limit that probability of detection to 0.1%. And then after that, I can evaluate these other amplitudes and see what probability of detection I get. So as an example, maybe 6 megawatts 50% of the time, and I'll detect a 10 megawatt oscillation 99.9% of the time. So this is how I'm kind of capturing the performance of the threshold, giving an indication of what the user can expect moving forward from when you start seeing oscillations. All right, so let's see what that looks like here in Archive Walker. First, I'll start with where I built that this thresholding approach into Archive Walker as well. So I'll show that first. So here I've got my same 4 signals, setting thresholds for band 1 and band 2 here, giving it the duration requirement of 30 seconds. Here I'm saying that the largest nuisance amplitude that I want to think about is 6 megawatts. I'll be able to, you can evaluate lower amplitudes as well. So that's an upper limit. 100 realizations, model order for that autoregressive model of 45. And then a 20-minute analysis window. So that's the setup, and then you would run this across the 2 days of data, and that's already been done. So now I'll jump to what it looks like when you've, after the fact, when you've analyzed those 2 days of data to do all that bootstrapping that I talked about. And now set this up with so here what I'm saying is for band 2, this has to do with the detector that's in Archive Walker, but it's for band 2. This will write it out to a file. I'm saying I want a nuisance amplitude of 3 megawatts with a associated probability of detection of 0.001. And then I also want to look at these probabilities. What amplitudes will I detect with these probabilities? So now it's going back and it's using all that information about that I collected over the 2 days to generate these thresholds. So we have these 4 thresholds, and each one, it's giving you a threshold that will now avoid alarming on anything less than 3 megawatts. It's accounting for the duration requirement. And so we get these thresholds. And then down here, what it's showing, again, this is 0.5, 0.9, and 0.999. So what this is saying is that for signal 1 with this threshold, you'll detect a 6 megawatt oscillation 50% of the time, a 7 megawatt oscillation 90% of the time, and a 9 megawatt oscillation 99.9% of the time. So it's again telling you what that threshold will do. It's predicting it for you to capture its overall performance. Now, if we look at signal 3, we're trying to avoid alarming on 3 megawatt oscillations, but this is saying that 90% of the time you're going to detect a 4 megawatt oscillation. And we say, well, I don't want that. That's too close. So this is where it's really helpful to have that insight ahead of time. So now we can generate new thresholds, and I'll do it for all of them, but you could just then use this threshold for signal 3, and now you won't start detecting oscillations until at least 6 megawatts. And again, that just has to do with the different characteristics of these signals that are different, and so we do need to do some tuning for those specific signals. So the last thing I'll do here is I'll now show, using those thresholds, what this looks like. And here I've for these, I've added I'm adding 4 oscillations, the 3 megawatts to start, so that nuisance amplitude, and then the three larger oscillations that were predicted by the outcome there. So signal 1, it crosses the threshold, but not for long enough, and that's exactly what we want. So we avoid the nuisance alarm, but we detect the next 3. Signal 2, avoid the nuisance alarm, detect the next 3. Signal 3, avoid it and detect the next 3. And signal 4, avoid the nuisance alarm, detect the next 3. So this is giving us the exactly what we're looking for, where we're able to avoid nuisance alarms, but then have predictable performance for those larger oscillations. Okay, so wrapping up, I just wanted to talk briefly about what this, so far I've been showing 4 signals, right? So does it scale? So I wanted to talk about what we did at Southern Company. The setup here is we had 130 megawatt signals and their corresponding 130 megavar signals. Southern Company provided 48 hours of data from December 2023. Again, same setup, 20-minute windows. So that's 144 models per frequency band. I've focused in this presentation on band 2, but I applied it to all 4 frequency bands with 100 trials per model. So this is not a small analysis, right? There's quite a bit there. But then the processing and archive walker, and I'm the first to admit that I'm not a software developer, so it could, I'm sure people with those skills could make this better. But even with at my skill level, I was able to keep this to 3 hours for that analysis. And so that's on where I showed you the settings page, and you run it across the 2 days of data where it's doing all the bootstrapping. That's what took 3 hours, and the storage at the end of that was 1 gigabyte. And the reason I would talk about storage there is we don't have to, all these, there's thousands and thousands of these realizations that we end up looking at across all these different signals. But we're not having to save all of those for the design process at the end. We just save a little bit of information, and so that works out to 1 gig of information. So very, very manageable there. And then when we go to actually generating the thresholds, when I was doing it for the 4 signals, it was basically immediate with clicking that. When we're doing it for hundreds of, 130 signals, then it ends up being about 15 seconds for each run. So to summarize that, it doesn't take much to set this up, and then you click run, and it'll run in the background for 3 hours. And then you can design the thresholds, at least have those initial designs within a couple minutes. So basically, within an afternoon, you could set thresholds for in this case, all of Southern Company. So very manageable as far as what's required. Once we had set these signals up based on data from December 2023, then we used data from oscillations that we've been detecting in ESAMs throughout 2024 to evaluate them. So, I'm only using 2 days to analyze the data. We're doing some work to figure out, is that enough? Do we need a little bit more? But the early result is that these thresholds are holding up months later. And so it's not like they only last a week and then you got to run the process again. We don't know exactly how long they do hold up and how often they need to be refreshed, but so far it seems like it's at least months later. The next step at Southern Company is to deploy these in RTDMS, kind of replace the thresholds that we're using before with these newer ones. All right, so to wrap up, again, this is, I dove into a lot of detail here, but I do think this is an important topic of making sure that when we have these commercial tools, we're able to set thresholds in a way that we're that where the people that are using them can rely on them to tell them about oscillations that they are interested in, and not pester them with alarms that aren't interesting for them. That's really important for tool adoption, and because of that, it's really important for reliable system operation. Um, the way I've tried to summarize this is that a good RMS energy threshold will avoid false alarms, of course, but also we need to think about nuisance alarms. And also we should be doing our best to offer predictable performance for these thresholds so that we know what types of oscillations we will be able to detect. And that so that we can make good engineering judgments about the trade-offs there. And so then a good thresholding method then I think is one that delivers that type of threshold, but also it needs to be able to support automation. It needs to be able to be implemented readily, and it shouldn't require excessive time, compute power, or storage. And so I'm hopeful that this newest approach kind of checks all those boxes and does this for us. And so my hope here is that this process or maybe a modification for it can be used alongside the existing commercial tools or within them to be able to provide these thresholds for utilities. And if not, and so I hope these methods and the lessons learned that I've shared today will be useful for the industry moving forward. So and I'll wrap up there. I'd be happy to take any questions.